Today let us see cavity resonators. So last class we have seen what are the cylindrical coordinators and cylindrical coordinate system we have introduced. So now let us see the cavity resonators. So as we have two types of waveguides like rectangular and circular, we have the rectangular cavity resonator and circular cavity resonators. So let us see the cavity resonators. Myself, Dr. V. Vijayasri Buliseti, Associate Professor, Department of Electronics and Communication Engineering. Coming to the outcomes of this session, at the end of this session, the student will be able to understand the operation of the rectangular and circular cavity resonators and can be able to derive an expression for the resonant frequency in the rectangular cavity and circular cavity resonators. Let us see first what is a cavity resonator. So we have seen different waveguides like rectangular waveguide and circular waveguide, where the wave is propagating along a particular direction depending on the parameters of the rectangular and circular waveguide. For example, if you take for the rectangular waveguide, we are considering that if we keep the broader dimension along x axis and the narrow dimension on y axis, then the wave is propagating along the z direction. So if we place any standing plate at the other end of this waveguide, so the wave hits this standing plate and reflects back, coming back forth. So that means the wave is moving back and forth, so hence there is a chance of producing the standing waves if we place the shorting place at a particular distance in the waveguide. So that is going to decide that whether that particular waveguide can act as a cavity resonator, can it produce the resonance or not. Anyhow, let us see first what is a cavity resonator. Simply like a waveguide, it is also a metallic enclosure which holds the electromagnetic energy. So electromagnetic energy means depending on the shorting plate distance and the dimensions, it may be the inductive or the capacitive, it holds the energy, electromagnetic energy. So when one end of the waveguide is terminated with a shorting plate, if we terminate with this shorting plate, there will be reflections that are producing by hitting this shorting plate. The wave by hitting the shorting plate can move back, okay, and hence there may be a possibility of producing standing waves. We call them as the standing waves. When another shorting plate is kept at a distance of multiples of lambda g by 2, that means when the wave that is reflecting back, if we place a shorting plate at this end also, then we are going to get the waves that are producing. That means suppose if this is the one end and if the wave enters at this and the wave go on hits the shorting plate and it produces the reflections, and so we are going to get the wave that is propagating, reflecting back, coming back. So such type of reflecting signals can be produced if we place these two shorting plates at a distance of lambda g by 2 or at a multiples of lambda g by 2. Then the hollow space so formed between these two shorting plates can be called as the cavity, and anyhow can support a signal that bounces back and forth. It bounces back and forth between these two shorting plates and produces the resonance. When the distance between these two shorting plates should be some multiples of lambda g by 2. Suppose if you take that t is a some integer, then if we take it as a some multiples of lambda z by 2, then we can produce the resonance. Okay. Anyhow, let us see the rectangular cavity resonator and a circular cavity resonator. So this is the broader dimension of the rectangular waveguide, and on this waveguide we are taking the dimension is broader dimension A, and this is the narrow dimension B, and this if we place a shorting plate here, this is, let us consider this is one shorting plate, and if we place another shorting plate at a distance, let us suppose this distance we are calling it as D, at a distance D, if we place another shorting plate, this is also a shorting plate, another shorting plate at a distance D, then if this D is multiples of lambda g by 2, then they produces the standing waves what we are seeing here. See, the wave moves to the back and forth, it is going to the forward direction as well as it is moving reflecting in the backward direction. So, if it is at a multiples of lambda g by 2, here we have taken that p is equal to 3, for 3 lambda g by 2 we are going to get the waves that are moving back and forth. Anyhow, one thing that you have to know that is that in a waveguide, in a rectangular waveguide or a circular waveguide, we are going to have half waves only, not a complete cycle of a sine wave, but only half waves are moving. So, we call this is the maxima and we call this is the minima. So, we are having this one successive maxima and minima are reaching to the shorting plate, and if this is 3 lambda g by 2, then there produces the reflected signal, and hence the wave moves, wave bounces back and forth and produces the resonance. So, the condition for resonance is the depth of the waveguide, that means where we are placing the shorting plates, the distance between the shorting plates should be the multiples of lambda g by 2, integer multiples of lambda g by 2. Similarly, if it is a circular waveguide, then also we have the two shorting plates. This is one shorting plate we place at one end, and this is another shorting plate we are placing at the other end. So, whose radius we are representing it as r, and the distance between these shorting plates we are representing it as L, or here also we can take it as a D, and the condition is same that it should be, this D should be, the hollow space between the two shorting plates should be always multiples of lambda g by 2. So, either it is a circular cavity resonator or a rectangular cavity resonator, the condition to produce the resonance is the distance between the shorting plates should be always multiples of lambda g by 2. So, now let us see, so what is this hollow space we call? So, in the cavity, I mean in this waveguide, the hollow space itself, that means the distance between the two shorting plates itself, we call it as the cavity, and the entire arrangement we call it as the cavity resonator. Whether it is a rectangular waveguide or it is a circular waveguide, the hollow space between the two shorting plates is called as cavity, and entire waveguide with the shorting plates together we call it as a cavity resonator. So, this cavity resonator is used to store the electromagnetic energy. So, the stored and electric magnetic energies inside the cavity are going to represent the inductance offered and the capacitance offered. So, if it is a magnetic energy that is represent, the amount of magnetic energy that is stored in the cavity resonator is represented with inductance, and the electric energy is represented with capacitance. So, this metallic enclosure may be a circular or a rectangular waveguide sections with these shorting plates closing at both ends, we call it as a cavity resonator. Okay, anyhow, a resonator can have infinite number of modes that are propagating through it, can produce the resonance, and of them a particular at a particular corresponding frequency we call it as a resonant frequency, we define it. Okay. So, that means when the resonance is produced at a distance d, where d is multiples of lambda g by 2, the resonant frequency occurred at this distance d, we call, the frequency occurred at this distance d, we call it as a resonant frequency. Okay. and when the frequency of an impulse signal is equal to the resonant frequency, then the maximum amplitude of the standing wave occurs. So that means suppose if we represent the resonant frequency as f naught, and if the frequency f, that means any signal omega or in terms of radians, and omega is nothing but 2 pi f, where f and if this f naught are equal, then we can say that the maximum amplitude occurs for the standing wave, okay, and the peak energies can be stored. At this case we may get the peak energies, whether it is magnetic energy or it is a electric energy, but we can get the peak energies when f is equal to the f naught. That means the modes that are depending on, suppose if you take a rectangular waveguide, it has the dimensions a, b, a rectangular cavity resonator, it has a dimensions a, b, d. Following these dimensions, in the coming part of the session, we are going to find what is the resonant frequency, which is a dependent of resonant frequency is a function of a, b, d, and also it depends on the mode of propagation, that is like m, n, p. That means where m and n, p are all are integers, it also depends as a function of m and p. So all this we are going to find out what is f naught, and if we are going to imply this frequency which is same exactly equal to f naught, then we can produce the maximum amplitude of the standing wave, or we also can say that the peak energies can occur at this moment. Okay. So the mode having the lowest resonant frequency, we call that particular mode as the dominant mode. So we also have defined what is the dominant mode here. So that means if we calculate the resonant frequency based on all these parameters, and if the resonant frequency is, for which mode the resonant frequency is less, we call that particular mode as a dominant mode. Okay. Now let us see how we are going to obtain the resonant frequency in a rectangular cavity. So for the rectangular cavity means already we have seen what is a rectangular cavity, how it looks. Anyhow, I will draw the rectangular cavity here for our reference once. So we take this is the broader dimension A, narrow dimension B, and of course we place a shorting plate at a particular distance d. So this is representing the d distance. So this is the rectangular cavity resonator. Okay. So to find out the resonant frequency, we know that the relation in the rectangular waveguides, that is h square is equal to gamma square plus omega square mu epsilon. This is the characteristic equation. So let us take the characteristic equation first, and let us find what is the frequency from this characteristic equation. But we also know that h square is equal to m pi by a whole square plus n pi by b whole square. So now let us equate these two terms, that is gamma square plus omega square mu epsilon is equal to m pi by a whole square plus n pi by b whole square, so that we can get what is omega square mu epsilon. Okay. So omega square mu epsilon can be taken it as equal to m pi by a whole square plus n pi by b whole square minus gamma square, where gamma is the propagation constant. Gamma is the propagation constant. So this propagation constant is generally represented as alpha plus j beta. Okay. This gamma is represented as alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. So that means whenever as we know that the rectangular waveguide acts as a high pass filter, that means for certain frequencies it allows the signals and certain frequencies it attenuates. So this gamma either may be equal to alpha or it may be equal to j beta. That means if it attenuates the signal, gamma is equal to alpha, and if it propagates the signal, then this gamma should be equal to j beta, that is phase constant. Okay. Anyhow, the condition for propagation of the wave is gamma is equal to j beta. So let us see, for a wave to propagate, this gamma should be equal to j beta. Let us substitute this j beta in equation 2. If I substitute this 3, gamma is equal to j beta in 2, we will get here as j beta whole square. Okay, we will get in place of gamma, we will get j beta whole square. So, that is j square beta square, where j square is minus 1. So, minus of minus will get plus beta square. So, omega square mu epsilon is equal to m pi by a whole square plus n pi by b whole square plus beta square. Okay. So, once we get the relation, then we also has to find out what is the beta, and so we can find out what is the frequency omega from this relation. So, let us see what is this beta. Okay. For a wave to exist in the cavity resonator, there must be a phase change corresponding to a given guided wavelength. So, guided wavelength we always represent it as a lambda. Okay. And we have that this lambda, how we have defined is lambda g is equal to 2 pi by beta. We have defined the guided wavelength in unit 1 while discussing the phase velocity, group velocity. We have defined this guided wavelength. So, lambda g is equal to 2 pi by beta, and so from this we can get what is this beta. So, beta we can get it as 2 pi by lambda g. So, beta is equal to 2 pi by lambda g, or we can also write it as pi by lambda g by 2, because the distance what we require between the two shorting plates should be multiples of lambda g by 2. So, let us obtain this 2 by lambda g as a 1 by lambda g by 2. So, this lambda g by 2 is going to represent the distance between the plates. If suppose we consider, that means suppose if you take d, already we have defined this d should be multiples of lambda g by 2, multiples of lambda g by 2. So, we can get the relation between d and p from this lambda g by 2, that is, so the distance between the shorting plates we have defined, it should be the multiples of lambda g by 2. So, d is equal to p lambda g 2, and from this we can get what is this lambda g by 2. So, what is lambda g by 2? Simply we can write lambda g by 2 is equal to d by p. Lambda g by 2 is equal to d by p, or in the denominator lambda g by 2 is there. So, simply we can write this beta is equal to p pi by d. Okay. So, we are going to get d is equal to p pi by beta, or beta is equal to p pi by d from this. So, the relation this beta is equal to p pi by d, we can substitute this in our frequency relation, that is equation 4. If I substitute, then we are going to get omega square mu epsilon is equal to m pi by a whole square plus n pi by b whole square plus p pi by d whole square. Anyhow, if you observe that we have replaced omega as omega naught square. Why we have replaced omega as omega naught square is when the distance is multiples of lambda g by 2, automatically the frequency that is produced is a resonant frequency, because we are going to get the standing waves that are moving back and forth and hence produces the resonance. So, we are replacing omega as omega naught here, while substituting the beta is equal to p pi by d. Okay. So, now from this we can obtain what is omega naught. So, omega naught can be taken it as, if you take mu epsilon to this side and apply the square root, you are going to get root 1 by mu epsilon n pi by a m pi by a whole square plus n pi by b whole square plus p pi by d whole square. Okay. So, what is this 1 by mu epsilon? We already know this, root 1 by mu epsilon is nothing but c. So, under root 1 by mu epsilon we can write it as a c out of this root, and so omega naught is also nothing but equal to 2 pi f naught. So from this we can obtain what is f naught by taking this 2 pi to this side. So we get f naught is equal to 1 by 2 pi root of this function, and this root 1 by mu epsilon we can write it as c. So we will get c by 2 pi root m pi by a whole square plus n pi by b whole square plus p pi by d whole square. And now in this also pi term is common in all the three terms, and so if you take this pi as common you will get root pi square as common, and the square and root gets cancelled and we are going to get pi out of this, and this pi can be cancelled with this pi. So f naught becomes c by 2 root n by b whole square plus m by a whole square plus p by d whole square. Okay, so this is the resonant frequency of the rectangular cavity. So this resonant frequency, now as we have seen earlier, that we have seen that this f naught is a function of a, b, d. Also it is a function of m, n, p. So m, n, p are representing the mode that is propagating through the rectangular waveguide, and a, b, d are going to represent the dimensions of the rectangular cavity. Okay. So now let us see the resonant frequency in the circular cavity also. Okay. So while coming to the resonant frequency in the circular cavity, here also we start our derivation from characteristic equation, where the characteristic equation is h square is equal to gamma square plus omega square mu epsilon, and from this we can obtain what is omega square mu epsilon, that is we can write it as h square minus gamma square. And for the propagation, here also we require the gamma should be equal to j beta, okay, alpha should be equal to 0, and then only the propagation starts. So as gamma is equal to j beta, if we substitute this j beta in equation 2, gamma is equal to j beta in equation 2, then we are going to get omega naught square mu epsilon is equal to h square, and j square beta square can be written as minus j square beta square can be written as plus beta square. So what is this h? But as we have discussed in the previous session, this h is going to have a different representation for TE modes that are propagating and TM modes that are propagating. Anyhow, from this let us first find what is omega naught and define what is h. So therefore omega naught is equal to root 1 by mu epsilon h square plus beta square, and so from this we get what is f naught. F naught is equal to 1 by 2 pi root 1 by mu epsilon h square plus beta, already we have derived, that is p pi by d. And now f naught is equal to, we can write this root 1 by mu epsilon as a c. So c by 2 pi h square plus p pi by d whole square. So this h in this resonant frequency is going to be a different value for TE and TM. See, in the circular cavities we represent the TE modes and TM modes with suffix as nm. That means we take it as TENM, or we represent TM as NM. Okay. Whereas in the rectangular cavity we have represented these modes as TEMN and TMNN. Okay. So now general representation or general notation for the modes is like TENM and TMNM in the circular cavity. So now the resonant frequency f naught is going to be differ, because the h for TNM is PNM dash by A, and for the h for TMNM is PNM by A. So as this h is going to differ, this h is equal to PNM dash by A for TE, and this h is equal to PNM for TM mode. So because of this the h is changing, this f naught can also changes, and this f naught is different for TE wave and TM wave in case of circular waveguide. But if you see For a rectangular waveguide, for a rectangular cavity, if we see, this is f naught is equal to c by 2 root m by a whole square plus n by b whole square plus p by d whole square. There is no change for TE mode or TM mode. So, this is the resonant frequency for both TE and TM modes, and the resonant frequency for the circular waveguide is differing for TE mode and the TM mode. So, let us see the summary of this session. So, we have derived what is the resonant frequency for the rectangular cavity, and we have derived the resonant frequency for the circular cavity. But for the rectangular cavity, the resonant frequency is same for both TE and TM, and for a circular cavity, the resonant frequency is going to differ with the propagating modes, that is for TE mode and for TM mode. Okay, so, sir.